All right, so we love diving deep into the stuff you send our way. And this time around, you've really outdone yourselves. We're talking wire electrical discharge machining, or WEDMA.
Yeah, pretty fascinating stuff.
It is. But I gotta admit, when I first saw all these terms, high speed, middle speed, low speed, honestly, my head was spinning a little. I bet some of you felt the same way, right?
I can definitely see that. Especially if you're just starting to explore WEDM, those labels can seem a bit, well, confusing.
Exactly. So that's exactly what we're tackling today. Think of this as your WEDM speed decoder ring. We want to strip away all the jargon and help you understand what those speeds actually mean in practice. Like, how fast does the work actually get done? How precise is each method? What about the cost? And most importantly, when would you actually use each one?
That's the key, right? It's not just about understanding the technology in a vacuum, but knowing how to apply it in the real world.
Exactly. We want you to walk away from this feeling like you can confidently choose the right WEDM approach for your specific needs without getting lost in the technical weeds. And you sent in some awesome resources to help us do just that. Pictures of the machines, tables, comparing the different types, it's all there.
Yeah, those visuals really help paint a clear picture.
Absolutely. But what we're going to do is bring those visuals to life through our conversation today. So, you can look at a table and see numbers, but we want to give you that context and understanding behind the
Right,
numbers.
because those numbers tell a story.
They really do. And speaking of stories, let's start with the one that's all about speed, high speed WDM.
Okay, so HS-WEDM, it really does live up to its name. What we see here is that it's all about very fast wire travel speeds. We're talking typically like 300 to 700 meters per minute. I mean, that's zipping along.
Wow, yeah. That's hard to even picture. That's so fast.
And to achieve that, they usually use a wire that can be used over and over again, made from either molybdenum or this blend of tungsten and molybdenum. It's called a tungsten molybdenum alloy. And the whole process uses an emulsion as the working fluid, like a mixture of oil and water.
Okay, so right away I see two big pluses there. Speed, obviously, and keeping costs down because you're reusing the wire.
Yeah, exactly. That high cutting efficiency and the reusable wire, those are the main drivers behind lower costs. You can get a lot done quickly without constantly needing to replace materials. But, and this is really important to remember, there's always a trade-off in engineering, right? So when you're removing material that quickly with a reusable wire, you naturally have less fine-grained control over the final product, the shape, and the surface quality.
So basically, you're sacrificing a little bit of precision for the sake of speed and affordability.
You got it. So with HS-WEDM, you generally see accuracy in the range of, say, plus or minus
Yeah.
0.015 to 0.02 millimeters. And the surfaces will be a bit rougher compared to the other methods we're going to talk about.
Gotcha. So, like, if I needed something super intricate with incredibly fine details, HS-WEDM might not be the best choice.
Probably not the ideal fit for that. But think about situations where you need to churn out parts quickly and keep the budget tight, high volume, maybe less intricate designs. That's where HS-WEDM really shines. It's like that reliable workhorse that just keeps going.
Right, makes sense. And you mentioned the reusable wire, the molybdenum or tungsten molybdenum alloy. That choice is all about making sure the wire can handle those high speeds and be used repeatedly without breaking, right?
Exactly. I mean, if the wire kept breaking, it would defeat the whole purpose of high-speed operation. Plus, constantly replacing wires would definitely drive up the costs.
For sure. Okay, so that's HSWEDM, fast, cost-effective, but maybe not the best for super high precision. What happens when you need something a little bit better in terms of quality, but maybe aren't quite ready to shell out for the most advanced equipment?
Oh, you're talking about that sweet spot, aren't you?
Exactly. It's like Goldilocks. This one's too fast, this one's too expensive, but this one's just right.
Exactly. That's where mill-speed WEDM comes in, MS-WEDM. And it's a really clever approach. They took the basics of HS-WEDM and basically said, okay, how can we get better results without breaking the bank?
Love that engineering mindset.
Yeah. So they often still use that reusable molybdenum wire, but the big innovation here is multiple cutting passes. Instead of just one fast pass, they'll do a roughing pass first to get rid of the bulk of the material quickly, then follow it up with one or more finishing passes. And those finishing passes, they make all the difference.
So it's like refining the shape with each pass.
Precisely. That's the magic of MS-WEDM. By incorporating those multiple cuts, they managed to get accuracy and surface finish way closer to what you'd see with the high-end, low-speed method.
While still being more affordable and going all in on the top tier tech.
You got it. Now, when you look at the specs, For MS-WEDM, you might see wire speeds that seem really high, like maybe 1 to 12 meters per second. That's because the machines themselves are capable of those speeds, especially during that initial roughing cut. But remember those finishing passes I mentioned? Those are done at much slower, much more controlled speeds. It's a bit of a balancing act.
So it's not just about raw speed anymore, it's about control and precision throughout the entire process. And what kind of improvements are we talking about here? Like how much better is MS-WEDM compared to HS-WEDM?
Oh, you definitely see a noticeable jump in quality. Accuracy can get down to something like plus or minus 0.002 millimeters. Think about that. 0.002 of a millimeter.
That's incredibly precise.
And the surface roughness, you might see it as something called Raman, that can get as low as 0.8 micrometers. So smoother surfaces, more accurate cuts. And all that while keeping costs more manageable than the top-tier systems.
Yeah, that makes MS-WEDM a really attractive option. I could see that, especially for things like making molds or any parts where you need good quality without needing absolute perfection.
Exactly. MS-WEDM is like that sweet spot for a lot of applications.
Okay, so we've covered HS-WEDM, the speed demon, and MS-WEDM, the quality-conscious middle child. Now let's talk about the big daddy, the one where you absolutely do not mess around when it comes to precision. Low-speed WEDM.
Ah, yes. LS-WEDM. This is where it gets really interesting. This method is all about achieving the absolute best possible quality, no compromises. So if you're working on something critical, something that demands the tightest tolerances, a practically flawless finish, well, LS-WEDM is your go-to.
We're talking aerospace components, medical devices, stuff where even the tiniest imperfection could be a big deal.
Exactly. Those are prime examples. And to achieve that level of precision, well, everything about LS-WEDM is different. First off, forget about those super high wire speeds we talked about before. LS-WEDM operates at a much more deliberate pace, usually around 3 to 15 meters per minute.
Wow, that's a huge difference compared to HS-WEDM.
Yeah, it's all about slow and steady wins the race here. But it's not just about the speed, it's also about the wire itself. With LS-WEDM, you use a wire that's specifically designed to be used only once. It's typically made of copper, which is a fantastic conductor of electricity, or brass, which offers a good balance of conductivity and strength.
So no reusing the wire like we saw with the other methods.
Nope. Single use only. And there's a good reason for that. Every time you use a wire, it degrades a little bit, it gets worn down. And even the tiniest amount of wear can affect the precision of your cuts, especially when you're dealing with these extremely tight tolerances. So by using a brand new wire for each cut, they basically eliminate that variable. You're guaranteed to get the best possible performance every single time.
Okay, that makes sense. And you also mentioned that LS-WEDM is even picky about the liquid it uses, the working fluid. Why is that?
Oh yeah, that's another key difference. For LS-WEDM, you can't just use any old working fluid. You need something super clean, super pure. Usually they use deionized water that's been meticulously filtered, or sometimes kerosene.
And that's all about maintaining those precise electrical conditions you need for such fine work, right? No room for contaminants or anything that could mess things up.
You got it. Deionized water, or kerosene in some cases, they act as insulators and coolants, helping to keep the whole cutting process stable. Plus, they help flush away all those tiny bits of debris that get generated during the cutting.
So basically, with LS-WEDM, you're controlling every single aspect of the process as tightly as possible to squeeze out every last bit of precision. And what kind of results are we talking about?
Well, let's put it this way. With LS-WEDM, you can get down to tolerances that are thinner than a human hair. We're talking accuracies of plus or minus 0.0002 millimeters, or even better sometimes. And the surface finishes, they're incredibly smooth, often with a roughness average, that RAV value we talked about of 0.8 micrometers or less.
Wow, that's truly amazing precision.
Yeah, it really is pushing the boundaries. But all that control comes at a cost. And I'm not just talking about the price tag on the machines themselves, although those are definitely more expensive than the high-speed or middle-speed options.
Makes sense. More complex technology usually means a bigger upfront investment. So where else do those costs come in?
Well, for starters, you're constantly using new wire, right? And those special wires, especially the coated ones, they can add up. Plus, you need sophisticated filtration systems to keep that working fluid as pure as possible, which adds to the operational costs. And then you have the maintenance and upkeep of the machines themselves, which, as you can imagine, with all that complex tech, it's not exactly cheap.
So it's kind of like having a high-performance sports car, right?
Yep.
It's amazing to drive, but you got to be prepared to pay for the premium fuel and the specialized maintenance.
That's a perfect analogy. So, yeah, LS-WEDM is amazing for incredibly precise work, especially for smaller parts.
Yeah.
But if you're trying to cut through really thick materials, it might not be the best choice. It all comes down to balancing those needs with the cost and the complexity.
Okay, so let's recap what we've learned about each method because I think it's really helpful to see them side by side. Luckily, the sources you sent in have this great table that does just that. It really highlights all those key trade-offs between the three approaches.
Yeah, that table is a fantastic visual summary.
So let's walk through it together. First up, wire speed. HS-WEDM is the speed demon, right? Hundreds of meters per minute. MS-WEDM is more moderate, and LS-WEDM is all about slow and steady.
Exactly. It's like a spectrum of speeds.
And then there's the wire material, molybdenum or tungsten molybdenum for the high-speed and middle-speed methods, but disposable copper, brass, or coated wire for LS-WEDM.
And that disposable wire is a big part of what makes LS-WEDM so precise, but also more expensive to run.
Right, because you're constantly using new wire. Then we have the working fluid, emulsion for the faster methods, super pure deionized water or kerosene for LS-WEDM.
All about keeping things clean and controlled.
Okay, now for the big ones. Accuracy and surface finish. HS-WEDM gives you the roughest results, MS-WEDM steps it up, and LS-WEDM delivers the smoothest, most precise cuts.
And those differences in accuracy are directly reflected in the cost of the machines. HS-WEDM machines are the most affordable, MS-WEDM machines fall in the middle, and LS-WEDM machines, with all their fancy tech, are the most expensive.
Makes sense. So basically, you get what you pay for. And finally, we have the typical applications. HS-WEDM for when you need things done quickly and cost-effectively, MS-WEDM for a good balance of quality and affordability, and LS-WEDM for those super-critical, high-precision applications where nothing but the best will do.
It's all about choosing the right tool for the job, right? Understanding the strengths and weaknesses of each approach so you can make the most informed decision.
Exactly. So if you're out there considering WEDM, remember, HS-WEDM is your workhorse for speed and budget, LS-WEDM is your precision instrument for the most demanding jobs, and MS-WEDM is that clever middle ground that tries to give you a little bit of both.
And don't forget, the best choice always depends on your specific needs. What level of accuracy do you absolutely need? How important is the surface finish? And, of course, what's your budget? Answer those questions, and the right WEDM approach will become clear.
And this idea of trade-off speed versus precision versus cost, it's something you see everywhere in engineering, in manufacturing, really in any field where you're trying to optimize something.
It's a fundamental principle.
So as you go about your work, or even just your everyday life, think about this. What other areas do you see this kind of trade-off triangle popping up? How can understanding these trade-offs help you make better decisions, choose the right tools, and ultimately achieve your goals more effectively? It's a framework that can be applied to so much more than just WDM. It's really about making smart choices in a world of limited resources and endless possibilities.
Absolutely. Food for thought.